Hey, this is Amber. Just wanted to go through an example of what it might look like to do week 20, which is solid shapes for the math map. And so this is just meant to give you a preview of what it might look like when I'm working with my class on this. So the first thing that we do is we start with our kind of like math warm-up game. And so this week we're still doing interesting integers, which is a handout on CC Connected that you can find. What I actually do is I set a timer on my phone for 5 minutes so that we're not spending any more than 5 minutes on this little opening game. And the interesting integer for today is the number 73. And so I would put the number up on the board and then ask them to start telling me about 73. And so they'll tell me it's odd, and they might call it a big number, although maybe not as big as last week was. They might say that they have an acute angle on the 7. They have straight lines and curved lines, so they might say something like that: straight lines, curved lines. And then they might get into more of the math definitions. So if you had 7 times 10, and then you had 3 times 1, that would be expanded form for 73. My purple's dying, so let me switch markers here. So they'll throw out a bunch of things. I'm not going to put up tallies for this. We like to tally when it's low enough. We can do the Roman numerals. Ooh, and I'm pretty sure that's L, X, X, 1, 2, 3. Because I'm pretty sure L is 50, because the Super Bowl is this weekend, right? And it's got an L in it. Okay, I'll make sure of that before I do it I go over it with the kids. That's some of the stuff that they might bring up. Another thing you can bring up, and this is just kind of interesting, this was mentioned in the interesting integer handout on CC Connected, and they talk about how this is Sheldon's number, and an interesting thing about it is I could ask the kids, so can you give me some of the prime numbers? And so you have 3 and 5, 7, 11, 13. So you keep going up. Well, if you go up to the 12th number, the 12th prime is actually the reverse of this, the number 37. And if you go all the way to 73, that's actually the 21st prime number in our series of prime numbers. So the reverse of this, 37, is the 12th prime, and 73 is the 21st prime. And I guess that's what makes it Sheldon's number. So kind of some cool, interesting things. So there you go. That would be what we would talk about for interesting integer. And if it hasn't been a whole 5 minutes, that's fine. We can move on to the next thing. We don't need to spend 5 minutes. I just have to set that as a limit, mostly on the weeks that we do number knockout, because they'll want to play that all day if they have an option. Okay, so then I say, open your booklets. Where are we this week? And I always have them identify where we are for the week before we start on the front exordium page. So they would open up their booklets. Theirs are still put together. I cut mine all up, and I like that as a director. But I think for the kids, it has been nice having them keep it together. I had my daughter keep hers together. But anyway, so they go into here, they look down complex, they see that we are on solid shapes, week 20, and we are still talking 3D. And so they might bring up those details, talk about that. Then we will look at the cover art. Okay, so now we're going to look at the cover. We're going to look at the artwork. And I would say the artwork this week is Conquest de Tenochtitlan, Mexico by Diego Rivera. What do you see? And they will probably point out that they see shapes. And so let them just define what types of shapes and what they're seeing. And they'll probably say they see people, and maybe they'll tell you about the Aztecs, and they'll tell you about ancient civilizations, especially if they've had younger siblings, because they've been talking about that in foundations. So you can let them just point out all the stuff that they're seeing. If they're not really talking, some of the things you can mention. Can you find these shapes? So pyramids. So the pyramids are these guys. Disc, which is just filled in circle. So maybe like the flat part of these buildings at the top would be disc. Cubes. So cubes, kind of like the squares, 4 sides. Actually, these maybe are a little bit more cube-like. Spheres, which are pretty much balls. I don't know that I'm seeing any shapes that are necessarily ball-like. Cones. These kind of look cone-ish. There's a cylinder on this center part. And then it says there's a icosahedron. And there's a picture of that in the chart, but I couldn't find it on this cover. So if you find it, let me know where it's at. So that's some of the stuff they've mentioned. And things to know is that these shapes have clear sides and boundaries, so they can all be measured. We can also measure something else about this image. This is actually a real place, or it was a real place. So it can be measured by latitude and longitude because it is an actual location. And then the other thing to kind of point out is you could start singing the song, Olmecs, Mayans, and the Aztecs, and see if it picks up for anybody. But their younger siblings have been singing that in foundations probably in the last week or two, and this is the location where the Aztecs were. So you can mention that the Aztecs were at Tenochtitlan. So there you go. The next thing that I always do is I read over the quote. I don't have the students read the quote and the reflection because a lot of times the language is above what they're used to reading and they just kind of stumble on it. So I just find it's easier for me to read it, but then let them talk about it. So I would read through the Isaac Newton quote. And then after that, I would say, so who is this Isaac Newton guy? And see if anybody remembers or knows about him. And if they're not quite, if you want to jog their memories or help them out, you can remind them of Newton's 3 laws of motion. And so we learned those in foundations. I don't know what cycle that is. I think maybe cycle 2 or 3. So it's been a little while, but I have a lot of CC kids who've been in it forever. So they'll probably be able to just restate the laws. But if they don't, I'll just kind of remind them. The first law was that objects at rest remain at rest and objects in motion remain in motion, unless locked by some other force. The second, Newton's second law of motion is that force equals mass times acceleration. So a force of something is the mass times the acceleration of it. And the third law is that every action has an equal and opposite reaction. So there you go. You can remind them of those things and tie it together for them. And then in this quote, this is kind of pulling from the contribution to the conversation on the next page. It says, Newton claims that God created all the shapes from the beginning and that all of them have a purpose. The Bible says God knew me even before he laid foundation of the earth. And he has begun a good work in me, which he will complete. So God has made all things with a special purpose. And then I go through and read the reflection. And so I would read all this, and then St. Augustine's just kind of describing that our weary souls need refreshment from God. So being sure to tie back to him. So that is probably it. Then I'd say, are there any other thoughts on how the cover page ties to solid shapes? Usually they don't say anything, but I always ask it. Okay, and then we move on to our first invention page, which is the I2 frame page. And we will be using this at some point, so I might as well just erase it real quickly. Okay, so I can say, tell me everything you know about solid shapes. And if they're kind of staring at you with a blank stare, then you could just be like, so tell me about cubes and tell me about spheres, because those are two examples of solid shapes. And then maybe that'll open up the conversation. They'll say more. So they can look on here, they'll give them an idea of shapes and stuff like that. If you need to kind of jog the conversation along, use the 5 common topics. So the first one is compare. So compare a diagonal to a diameter. And they can probably see on their sheet here that for a diagonal, we're talking about that diagonal line that goes across from one vertex to the other vertex, or one vertex to the other vertex on a cube-like shape. And diameter is that measurement from one end of the circle to the other end that goes through the center. And so that's the difference there on those two. Diameters are always congruent. So no matter where I draw that diameter across this sphere, it's always going to be the same length, right? But a diagonal isn't always going to be the same length, because if I did a diagonal from this corner up to this one, that might be different than this one, could be different from that one. So those are not always going to, they're not always going to be congruent. Okay, second common topic, define. So define polyhedral and dihedral angle. And so you can maybe see, I could draw it. I probably will actually draw this up on the board. If I draw my cube, and no, this is as good as my 3D shapes get. So, okay, so this bottom plane and this plane come together. And right here, you have 2 planes that come together. So the 2 are dihedral. And you can remind them that duo means 2 in Latin. Oh, maybe we haven't done numbers yet, so they may not know that. Maybe it's not reminding. Tell them duo is 2 in Latin. So di is usually in front of something when you're going to have 2 parts to it. And then this junction, and I might use a different color marker to make it stand out, but this junction where 3 angles come together is your polyhedral. So poly meaning more than 2, and so you have 3 on here. How does the circumstance of dimension change when a figure is open or closed? Okay, so I find this is the easiest one. So in 2D, here's my flat circular shape. Oh, I meant to grab my PVC piping. Okay, forgot my PVC piping. 2D, this is kind of a flat circle. The outer edge of it, it stays here. It can only stay in that 2 dimension. When you come into 3D, it's kind of like viewing this as a pipe that just like continues on and on and on. So you still have the circle, but you're continuing that. Okay, so this is flat. This one kind of continues like a pipe would do. I have duct tape in this example, but you kind of see that idea. That is how this circular shape would continue. Now, the other thing, if you want to, that's so unbounded, that's how it looks. But if you want to consider what a bounded shape would be in 3 dimension like this, then we have to look to a sphere. Because now this is bounded, it's all contained, it's a closed shape, solid shape. Okay, so that's kind of the difference we're trying to get at here with these. And that's what I find is the easiest one to kind of explain it. There's other examples on how a shape is unbounded it's bounded in 1 dimension, but when you jump up to the next dimension, it becomes unbounded. And so then the shape maybe has to change to become a bounded shape in that dimension. And they give some other examples on here. But I thought this might be the easiest one to understand. Okay, and then relationship, next common topic. So the relationship between equator and meridian. And they're probably starting to discuss this because we've been drawing maps all semester. But you can have them even remind you, okay, so where's your equator at? And, you know, someone might even want to draw it. And they'll kind of point out that their equator's right here, equidistance from the North Pole and the South Pole. So that's equator, and then meridian lines go from North Pole to South Pole. And so they're kind of perpendicular to that equator line. And I intentionally didn't draw it straight. You could draw a straight one, but those. Okay, so there's your meridian lines. So just pointing that out to them. And then the last of the 5 common topics, if you want to discuss, and of course, I don't always cover all 5 of these. I just put them in my notes because Dr. Gilpin mentions them, and so I just put them in there. You can choose which 1 or 2 or however many you want to go through with your class. But the last one she talked about was, so for authority testimony is, how does the choice of the base determine the height of the object? And so when we were back at that polyhedral shape, okay, so if I say this part is the base, then I'm probably saying that this is my height. But if I was calling this side, this face over here, the base, then that probably means that this length in that direction is my height. So wherever your base is for your shape, that's determining what your height is. And it could change. I wouldn't maybe necessarily use this as my height again, because I need to pay attention to which one's the height that attaches to the base. And so it changes it becomes the authority for what you use for height. Okay, that's all that means. Then the next thing to do is head to the Memoria and arrangement page, and lots of symbols, lots of shapes. There's a couple of good equations at the top of this, and those are useful equations for them to know. So maybe that's worth memorizing. Kind of getting a feel for what these shapes are. I think 2 of the big things to notice is that anything that has pyramid in it, you have that base, and then as you're having your faces, your sides come up from it, they all meet together at a single point. Okay, so that's how the pyramid happens. Versus you have your base, your shape sides come up and they maintain those sides. They maintain that shape, and that's what you get with a prism. So the difference between the prism and the pyramid, that's probably another big thing to just kind of point out that they can understand. And then on the charts are really fun. There's a lot of shapes and some great geometry, definitions on stuff, couple of unit measurement stuff and conversion factors. So they have some of that in their student problems, and this is where they can go to find that. That's page 3 of the charts. And then some fun ideas on how shapes actually lay out if you flatten them out into a 2-dimensional plane. And they have some examples of that too, like which shape is the soccer ball and which shape is a soda can. And so they can use this to help them out on that. Couple things to know is, so closed means the figure is bounded in the dimension. We talked about that, but that when you go to the next dimension, it becomes open or unbounded. And so in my mind, and I hope this is right, I'm viewing it that bounded and closed and solid are pretty much all still meaning the same thing, at least for the purposes of what we're doing this week. So hopefully that's correct in my understanding, because I'll probably interchange those words and I'll tell them that they're meaning the same thing in our case. And then also maybe point out to them to harness the power of the language. So because they're learning Latin, they're learning a lot of great ways to dissect language and understand what something means. So like if you have dodecahedron, okay, we already discussed that do is from Latin duo, and it means 2. And then deca is 10, like a decade. And then hedron's actually from I had to look this up. This is because I didn't recognize it from anything in Latin, and it's because it is a Greek word, and it means faces. Faces, and so in this case, it's kind of like the faces or the sides of the shape. And so from this, you can say it's 2 and 10 faced solid. which, so 2 and 10 is 12. So 12 faced solid shape. And they have an example what that looks like in their charts. And I think on the invention page, they have that one too. And then another example of using their language is pentagonal pyramid. Pentagonal pyramid. And we already discussed how pyramid just means that all of the sides come to one vertex, come together at one point. So all sides connect to one point. And then penta is from the Latin, and that will mean 5. So 5-sided shape coming to pyramid. Okay. Next part, so the rhetoric part. So aha moments from last week. I don't always usually have that. I ask them if they want to go through anything on last week. They never do. But now we go through the problems for this week. And usually I let my kids work in groups of 2. And then because we have 7, we'll have one group has 3 to it, unless somebody wants to work alone. And sometimes they do. They're like, I'm fine, I can work alone. And that way we cover all 4 tops of the pages. And so the first one, and I kind of go through in the lesson plan how you can go through this in detail, but I go through and let them go ahead and work on their own. And so this, they're just pretty much tracing and they're filling in where's the faces, the vertices, and the edges. And it's really cool for them to kind of show where these are and explain to their colleagues, this was the edge, this is the vertice, this is the face, and show that they can do it. And then they're seeing Euler's formula. And so that's faces plus vertices minus the edges will always equal 2 on a closed shape. So you can do that then with their calculations on these. And again, that's pronounced Euler. And so 2 of them will go through this. And what I actually do is I'll just put these little sample shapes on the board and then have a spot for faces, vertices, edges. And then they can come in up to the board once they've worked through it with their partner. I usually give them about 5 to 10 minutes to work through it together. And then they come up and they fill in the answers on the board. And we do that so that everybody can go back to their seats and then see the answers and fill it out and have some of their math map work done before they're going home for the week and working on it at home. The next page to notice is we have solid shapes, but now we're talking about spheres. So, we have a sphere here. And then this is called a torus. And I didn't know that. So this is this 3D shape, which has like a ring. But it reminds me of a bullfighting ring, and bull is toro in Spanish. So if you happen to know that, it might help you remember Taurus. That's how it's helping me. The other thing to point out is once they work through this map, or their math, so like over here, they're showing that the surface area is 4 pi r squared, and so the r is 6 centimeters. So they're plugging in 6 here, and they're squaring that. They're going to get it to 36, and then they'll multiply the 4 and the 36 and get to 144 pi. And be sure they see that pi stays as pi for the whole thing. So these are rational numbers. We don't break them down to their decimal part or their closest approximation to decimals, because that's the math loses its exact measurement the more that you do that. So when they're working with these irrational numbers, they're going to leave them in that irrational form. So pi will stay in pi form throughout here. So just kind of point that out to them that they're going to do that. And then there's the third page. Again, they're picking out what kind of prism these are, and they're going to solve this, and they're actually going to find they get the same exact answer, whether it's skewed and oblique and the angles are kind of off to the side, or it's straight up. It's still the same measurements, at least for the purposes of what they're measuring here. There will be time, they won't always have right measurements, but for this, it's all the same. And then on the fourth, engineering drawing, so they're really just plotting out and drawing like the height is 2, so they just go up by 2 of the little steps. Width is 3, so they just go over 3 of the little dots. It's kind of like a connected dots, but they're building this same shape over here and seeing how that works. And then for the longitude and latitude, they're just matching where things are north and south, and then the east and west, and finding where those points are on the globe. So that's it. I think it's a pretty fun week. Do I have any other notes? No, I don't have any other notes. Remind them about their Seeing the Unseen booklets. Maybe ask if anybody has anything new that they've added in there. And then you can go through the catechism, just asking them where do they find the answers, where do they get other help, stuff like that if they don't know. But I'm pretty sure most of our kids know by this point in time where to go and what to do. So I guess if you have a little bit of extra time, you can work through other problems here. Or there's a really fun Howie Hua, who's a math professor, college math professor. I follow his stuff. The Math Map page on Facebook will often show his stuff, but he has a really cool way to make two hearts that interconnect. And so they're little Mobius strips, which are like where you go around the strip, but it never has an end, because it's not like there's not one side and a second side, because the sides come together, and so it's just a continuous line. So that's a Mobius strip. He puts two of them together at a right angle, and then he cuts them in half, and then you pull it apart and you get these two interlocked hearts. So I'll link to that video down below. Because it's Valentine's Day this week, if I had enough time during math, I thought that would be a fun activity for the kids to do, and so I'm hoping to do that, but we'll have to see how our time goes. But I'll link that below in the comments so you can find it. Okay, thanks for watching.